In last class we will discuss about the types of magnetic materials. So mainly we discussed dia and paramagnetic materials. Today we will discuss about ferromagnetic materials. Okay, ferromagnetic substances are ferromagnetic materials. Okay, now coming to the, if you go into the paramagnetic materials, so paramagnetic materials are temperature dependent. So if you increase the temperature, that magnetism will be either increases or decreases, depends on the type of material. Okay, now similarly diamagnetic material substances does not depends on temperature. Diamagnetic material is does not depend on temperature. Okay, so and now coming to the, because why we are saying here paramagnetic material is temperature dependent means at very lower temperatures, at very lower temperatures, these paramagnetic materials will behave as a diamagnetic material. Already we discussed about in case of superconductors. So if you reduce the temperature of the at room temperature, if you will take at room temperature, the superconductor will exhibit the paramagnetism. Okay, paramagnetism. If you reduce the temperature, at a particular temperature, what happens, that paramagnetic material will become so diamagnetic material. Okay, so that's why we said that these paramagnetic materials are temperature dependent, but diamagnetic materials are does not depends on the temperature. Okay, now coming to the already we discussed about the this mobility and chi. So those are the important. So how it will be, so mobility and susceptibility values for para and so dia as well as ferro also. Okay, now we will discuss about the main ferromagnetic substances. The substances which when placed in magnetic field become strongly magnetized in the direction of field are known as ferromagnetic substances. Okay, so if you place the magnetic ferromagnetic material in the magnetic field, what happened, so it will be magnetized in the direction of the applied field, magnetic field, these type of materials. So in case of paramagnetic material also, so those are magnetized in the field direction, but so that magnetization is very less. Here in case of ferromagnetic material, that magnetization very highly magnetized, strongly magnetized. Okay, so in case of ferromagnetic substances, so these type of materials we will call it as ferromagnetic material or ferromagnetic substances. Okay, now if you observe the atomic level, that means microscopic level. So microscopic level, each atom will act as a one dipole. It's have permanent dipole momentum in case of ferromagnetic material. So in each atom will act as, all type of materials, each atom will act as a one dipole. Okay, so if you will take especially ferromagnetic material, so that those having permanent magnetic momentum, ferromagnetic materials having permanent magnetic momentum. But if you will take without applying any external field, so suppose iron is an example for ferromagnetic material, so it is not magnetized initially, it is not magnetized. What happened, if you bring to the, so any other iron piece, it will not attract. Okay, so because what is the reason means, so it's have permanent magnetic dipole moments inside, but so those dipoles are oriented randomly. Yeah, I will explain you. See here. I'm taking, so this is the here. Okay. So this is the one magnetic material I am saying. So these in this there are different domains will be there in case of ferromagnetic material. We'll discuss the domain theory also. We will discuss the domain theory. Okay, so if you will take each domain, that domain orient in this atom, number of atoms in the presence in this domain. Suppose 10 atoms will be there in that domain, means all 10 atoms will be orient in a particular direction. Each atom having particular dipole moment, and so because of magnetic dipole moment. So that means because of that magnetic dipole moment, so what happened? One side it will act as a north pole, and the side it will act as a south pole. If you will take this domain, what happened? So this domain having particular magnetic field. Okay. So if you will take another domains have orient in a different direction, not a similar to the this one. Okay. So different direction. So this direction. Okay, so like that, if you will take another domain, so another domain orient in a another direction. Okay, so like that, different domains will orient in a different direction. That's why, so resultant magnetic momentum, if you will take a total substance, if you will take a bulk substance, resultant magnetic momentum of the ferromagnetic material is zero without applying any external magnetic field or without magnetization. Without magnetization, what happened? Resultant magnetic momentum of the ferromagnetic material is zero. Okay, so those are having permanent dipole moment. Dipole moment means each atom having some magnetic field. Each atom will act as a one dipole. Each atom having dipole momentum. There is a permanent dipole momentum for each atom. But if you will take bulk material, so those are cancel out with each other because different domains will orient in a different atoms will orient in a, those dipole moments orient in a different directions. Okay, so these all atoms will form like a one domain. So these all atoms are orient in one direction. These form like a another domain. So similarly, uh, some atoms, yeah, some atoms are oriented in this direction. So like this direction. Okay, these are all domain, all atoms combinedly form a one domain like that. So different materials will orient in different atoms will orient in a different direction, and they will form like a domains. Okay, so if you will take resultant magnetic momentum will be cancel out with each other. So the resultant magnetic momentum is zero without applying any external magnetic field. Okay, this is in case of ferromagnetic material. Now, what is the best example for ferromagnetic materials are ferrous, cobalt, nickel. Ferrous, cobalt, nickel. So these three are the best examples for ferromagnetic materials. Ferromagnetic materials, and so compounds of these ferrous, cobalt, nickel also some examples compounds of this ferrous, cobalt, nickel. So ferrous, cobalt, nickel as well as those compounds will exhibit the ferromagnetism. Ferromagnetism. Okay. Now coming to the properties of the ferromagnetic material. There are attracted by the magnets. If you place these ferromagnets in a magnetic field, what happens? So those are attracted by the magnets. Uh, they possess all the properties of paramagnetic substances with which greater intensity. So whatever the properties we discussed in the paramagnetic materials, so those all properties are exhibited by this ferromagnetic material, but intensity is high. That means these values, so suppose if you will take chi value and mobility value is very high. Okay, and the susceptibility of a ferromagnetic substance decreases steadily with rise in the temperature. So that means these magnetic property, ferromagnetic properties depends on the temperature. Ferromagnetic properties depends on the temperature. So if you increase the temperature, what happen? So it will loses the ferromagnetism. At a particular temperature, it will loses the ferromagnetism. At which temperature that ferromagnetic will material, that means it loses the ferromagnetism, and it will become a paramagnet. At which temperature? So that ferromagnetic material will become a paramagnetic material. That temperature we will call it as Curie temperature. Okay, understood? So ferromagnetic material is with increasing the temperature that it will loses their ferromagnetism. Ferromagnetic materials are loses their ferromagnetism with increasing the temperature. At a particular temperature, that ferromagnetic material will become paramagnetic materials. Those temperature will called as Curie temperature. Understood? So this is about the Curie temperature. So the formula will be chi is inversely proportional to the temperature. So that means susceptibility value. So with increasing the temperature, what happens? Susceptibility value is reduces. Susceptibility value is reduces. That susceptibility chi value is very greater than 1 for very greater than 1 for ferromagnetic materials. So mobility. So mobility also, yeah. So here chi value is very greater than 0. Chi value is very greater than 0. Mobility value is very greater than 1. Mobility value is very greater than, sorry, permeability value is very greater than 1. Permeability value is very greater than 1 and susceptibility value is very greater than 0. Okay, so that susceptibility is inversely proportional to the temperature. With increasing the temperature, susceptibility is decreases. See, this is the Curie constant. Here Cm is there, na? That is the Curie constant. Okay, and T is the absolute temperature. So at a particular temperature, that ferromagnetic material will become the paramagnetic material. The temperature we will call it as so Curie temperature. Curie temperature. Okay, so this is about the ferromagnetic materials. Okay, and we will discuss about the ferro and anti-ferromagnetic materials. So ferromagnetic materials and anti-ferromagnetic materials. Before going to the discussion of this ferro and anti-ferromagnetic material, so I will explain just fundamentals of how magnetism will. So okay, see here. According to, we know that if this is a circular coil, if current is passing through the circular coil, what happens? So magnetic field is produces. Magnetic field is produces. Okay, same concept here also. So if you will take any atom, so what happens? So that atom contains, so nucleus, around that nucleus electron is revolving. Electron is revolving. That means electron having orbital motion as well as spin motion. Electron having orbital motion as well as spin motion. If electron is revolving around the orbit means, so due to this orbital motion, that means this is the circular motion only. Circular motion means, so current carrying to the circular coil. So that because of the current carrying to the circular coil, what happened? Magnetic field is produces. Like that only here also. So current is so moving like a circular coil. So because of this orbital motion, what happened? Some current is produces. So sorry, because of that current, what happened? Magnetic field is produces. So that magnetic field is, so direction is n. One side it will act as a north pole, another side it is act as a south pole. Due to the orbital motion of the electron, what happened? Magnetic field is produces. So that is, so one act as a north pole, another one act as a south pole. So if you will take diamagnetism, is mainly occurred due to the so orbital magnetic momentum. Diamagnetism is so mainly due to the orbital magnetic momentum. When you apply the external magnetic field here, what happened? These orbital magnetic momentum change their direction. So because of the changing of the their direction of the electron, what happened here? That what so previously, so it will be magnetic field will be oriented in the opposite direction of the applied magnetic field. Okay, that's why it will, the diamagnetic material is repelled by the external magnetic field. Okay, so that means diamagnetism is mainly due to the orbital motion of the electron. Okay, now coming to the, okay, if you place the dipole in a external magnetic field, what happen? So some force is act on that material. So some force, that force will be like this. Okay, because of this force only, so torque will be act on that. So because of the torque, so it will change the direction. Okay, now coming to the so yeah, what is the main reasons for magnetic momentum? Is already we discussed about the orbital motion of the electron, as well as nucleus also. Nucleus also having so some spin. So because of the spin nucleus also, so some magnetic field will be generated. So that is negligible. Due to the nuclear spin also, some magnetic field is generated. That is negligible. So first one is the orbital motion of the electron orbital motion. Here there is no nucleus. So orbital motion of the electron orbital motion. So due to the orbital motion of the electron orbital motion, as well as electron spin also. So electron spin having positive spin as well as negative spin. So positive spin, due to the positive spin, what happened? So south pole will be formed on this side, and now north pole will be formed this side. If you will take spin is minus half means, so these poles will be opposite direction of the previous one. So the south pole is this side and north pole is this side. Okay. Due to nuclear spin also, some magnetic field will be produced. So that is negligible. Okay. Now coming to the, if you will take paramagnetic materials. Paramagnetic materials means so in case of paramagnetic materials, mainly that paramagnetism is mainly due to the spin. Mainly due to the spin orientation of the electrons. So mainly due to the spin orientation of the electrons. Okay. So diamagnetism is orbital motion of the electron. Okay. Now, so orbital motion means when you apply the external magnetic field, that orbital motion will be oriented in a opposite direction of the applied magnetic field. Then it will be exhibit a diamagnetism. Okay. So if you will observe that, so if you will take any material, there is a little amount of diamagnetism will be there, but other magnetism. So if you will take oxygen having paramagnetic material, in that oxygen also there is a little amount of diamagnetism will be there, but so that paramagnetism is overcome the diamagnetism. That paramagnetism is so dominates the diamagnetism. That's why it's we did not observe that diamagnetism. Okay. So in case of ferromagnetic material also, ferrous cobalt nickel, so how they will exhibit means due to the spin as well as orbital motion. So due to the spin, so that paramagnetism will be due to the nuclear spin, electron spin, as well as the electron orbital motion. So how it will be means, if you will take ferrous, so in that ferrous orbital motion, so due to the electron orbit, what happened, magnetic momentum will be produces. So that the magnetic momentum is oriented in a field direction. That means some orbital magnets are oriented in a field direction. Okay, that because of that orientation, what happened, so it will be magnetized in the direction of the field direction. Similarly, spins also, electron spin also, so in the field direction only. Okay. That is the reason for magnetization. Okay. See, so here, so what is the magnetization? Means, here m is the magnetic dipole momentum. Already we said that each atom will act as a one dipole. So here m is the magnetic dipole momentum. We are taking here average magnetic dipole momentum. So magnetization is nothing but so already we said that sometimes we will discuss about that. So that material is magnetized. Means, so all atoms are oriented in a particular direction. That means resultant dipole momentum is very high. That means, so here, so capital M is equal to n into small m. Small m is the dipole momentum, average dipole momentum. Okay. Now coming to the, so n is the number of dipoles per unit volume. If you will take one material, so in that material you will take the unit volume, how many number of dipoles will be present. So that is the capital N. Here that magnetization means, so dipole momentum per unit volume. So here m is the dipole moment, average magnetic dipole moment. If you will take a dipole momentum per unit volume, that is the magnetization. dipole momentum per unit volume, that is the magnetization, capital M. Okay. Yeah, so there is a relation between so chi and M. So chi is equal to M by H. Okay, that is the magnetization versus. Okay. Now coming to the already we discussed, and types of magnetic material also we discussed here. So mainly dia, para, ferro and anti-ferro and ferromagnetic material. We will discuss about the so this anti-ferro and ferromagnetic material. Ferromagnetic, yeah. So mainly, so first of all, we will discuss about the ferromagnetic material based on the domain theory. Based on the domain theory, they will ask specially. So explain the domain theory. Okay. So domain theory means so we have to discuss about the so domain theory first. Yeah, ferromagnetic materials are materials include iron, nickel and cobalt and components containing these elements. So best examples, main examples are ferrous, cobalt, nickel. Ferrous is nothing but iron. So cobalt and nickel, these are the best example for ferromagnetic material as well as these compounds. That means so material prepared with so these ferrous and cobalt and nickel. Okay, so those are also exhibits the ferromagnetism. In the absence of applied magnet, already we discussed, in the absence of applied magnetic field, each atom has a very strong magnetic dipole moment. So if you take those atoms are having strong magnetic dipole moment, okay, but if you will take resultant dipole momentum is zero. Resultant dipole momentum is zero. Regions of many atoms with aligned dipole moments called domains. Already we'll discuss that. So many dipole each atom, so here there are so many dipoles. Okay, so these are will act as a these are the domains. If you will take each domain, see here, so this is the one domain. So here only represent with single line, so this is the one domain. In that domain all these are the dipoles. All dipoles orient in a particular direction, one is single direction. Okay, that means each atom, single atom act as a one dipole. This shows single atom act as a one dipole. All dipoles are orient in a same direction. If all atoms are orient in the same direction, that area we will call it as domain. If you will take this domain, so all atoms are oriented in this direction. Similarly, so like this, all different atoms, so different atoms are oriented in different direction, so those combinedly form as a one domain. Okay, so different domains will orient in a different directions. Different domains will orient in a different directions, so without applying any external magnetic field. So that's why, so what happened, resultant magnetic momentum, that means domains are oriented randomly, that's why resultant magnetic momentum is zero. Okay, now coming to the yeah, so if you will take permanent magnetic momentum, permanent magnet means, so here resultant magnetic moment is oriented in a particular direction. So some domains are oriented in different direction, but resultant magnetic moment will be so contain one particular direction. That's why those will exhibit, those material will exhibit, so without applying any external magnetic field also, permanent magnetic materials will exhibit the some magnetism. Permanent magnetic materials will exhibit the some magnetism, because so there is a some resultant magnetic momentum already present inside the material. So that's why, so permanent magnets are like this. So see here, so three-dimensional picture of the domains, three-dimensional picture of the domains here. If you will take a unit cell, this is the unit cell. In that unit cell there are so many number of domains will be present. See here. Now coming to the so magnetic domain. Okay, so if you will observe the so domain, so that domains are oriented in a different directions here. So those domains are separated by a one wall, so that wall we will call it as domain wall. Domain wall. Okay, one domain is separated by the another domain, so that domain we will call it as the in between the those domains there is a wall will be there, that is the domain wall. See here, so these are oriented in a different direction, these are oriented in a different direction. In between there is a domain wall will be there, in between also there is a domain wall will be there. Okay, now if you apply the external, so the domain wall, if you observe closely, that means in this domain wall how atoms will be oriented, how atoms will be oriented, or dipole will be oriented means okay. So in this domain, so just we will discuss about these two here. So nuclear all dipoles are oriented in this direction. In this domain, all dipoles are oriented in this direction. In domain wall, how those will be oriented means, see here. So initially nearer to the water wall, nearer to the this wall, this domain. So this domain, what happened? So that spin will be so approximately equal to the this side. Similarly, while going through the another side, what happened? That domain, that direction of the dipole will be changes. Okay, after reaching the another wall, another side of the wall, so the domain particularly orient in the another direction. That means that here dipole is orient in the another direction. That means inside the wall, so that orientation will be like this. Inside the wall, that orientation will be like this. Okay, now so this is the real scenario of the domain. So but generally we will consider as a, so this is a one domain, this is another domain, in between there is a wall, so that wall will be present like this. Okay, so this is the, so how domains will be orient. So that means here gradual transition takes place from one domain to another domain. So there is a no sudden change, just gradual transition from one domain to another domain. Okay, so that orientation is changes gradually, not suddenly. Okay, the overall magnetization of the material is vector sum of the magnetization vector of all the individual domains. See here. So already, so we said that capital M means so magnetization per unit volume. Okay, so small m, here each atom having so magnetic dipole momentum, that is small m. Here number of atoms will be there means magnetization is capital M is equal to n into m. Okay, if you will take so vector sum means so here magnetic momentum direction is this side, so here magnetic momentum direction is, yes, someone is unmuted, mute yourself. Yeah, so here vector sum we will take, so magnetic momentum direction is above, here below, this is this side, so we will take the resultant magnetic momentum, that means vector sum of the magnets we will take. Yeah, now coming to the ferromagnetic materials. So already we discussed about that chi is very greater than 0, mu r is very greater than 1. Okay, so these are strongly depends on the temperature. Magnetic materials are strongly depends on the temperature. With increasing the temperature, those material will lose the magnetism at a particular temperature. This ferromagnetic material will become the paramagnetic material. So at that temperature we will call it as Curie temperature. Okay, now coming to the domain orientation. So if they ask domain theory means you have to write this all. So particularly they will ask domain theory. So domain theory means you have to explain this all. Okay, now coming to the domain orientation. Yeah, so in case of diamagnetic material, so here what is that flux density B value? So how B value will be oriented? So this is in case of vacuum. So if you will take in case of vacuum, H versus B, that curve will be like this. So if you will take diamagnetic material, so B versus H curve will be so below the, and that means this is a in case of vacuum. So that in case of diamagnetic material, so B versus H curve, H line will be like this. So below the vacuum. If you will take paramagnetic material, just above the vacuum. So if you will take ferromagnetic material, so it will be suddenly increases. That means magnetized. It will be, so B is the magnetization, induced magnetic momentum. With increasing the H value. So what happened? That induced magnetic momentum suddenly increases. Okay. So this is in case of different dia and para and ferromagnetism, how BH curve. That means not BH curve exactly. That means if you will take that is loop. If you will take loop is different, curve is different. This is just curve. So that is the loop. Okay, loop means we will discuss about the all directions. But here we are discussing about only one direction. Only one direction. Okay. So how it will be? So with increasing the H value, how B value will be changes in case of ferromagnetic material. Okay, so initially without applying any external magnetic field, all domains are oriented in a randomly. All domains are oriented in a randomly. That's why. So what happened? Magnetization. B value also 0. B value also 0. Now if you will increase the applied magnetic field, so what happened? Certain magnetic uh, in, certain dipoles will orient in a field direction, not all, only some. And that means, so if you will take field direction is this one, so in that field direction what happened, domain is increases, length of the domain is increases, remaining direction length of the domain will be decreases. See here, so here, so all domains approximately, all directions domain length is approximately equal. But if you will take here, so in the field direction, approximately along the field direction, domain length is high, so remaining direction domain length is very less. Okay, if you increase further, so similarly domain length is increases in the field direction, remaining direction domain length is decreases. That's why what happened, so B field is oriented inside the material, so that dipoles are oriented in a field direction. So if you increase further, what happened? See here. So all domains, maximum all domains are oriented in a along the field direction. So opposite direction it will be vanishes. It will be approximately vanishes. See here, if you increase further, so all domains combinedly form as a one single domain. All domains combinedly form as a one single domain. So after that, if you increase the further H value, what happened? So that all domains orient in a field direction. All domains orient in a field direction. There is no other domains to orient in a field direction. That's why what happened? B value will become saturated. B value will become saturated. Okay. So this is about the how domains orient in a along with the so applied field. If you increase the applied field, what happen that opposite domains area will be decreases. So along the field direction domain area is increased. So at a particular applied field, so all domains will become a single direction. So after if you increase further means all domains orient in a along the field direction. Okay, that's why. So this B value will become saturated. That magnetization value will become saturated. Okay, this is the unit here. Okay, now that is about the domain theory of ferromagnetism. That is the domain theory of ferromagnetism here. Now coming to the, we will discuss about the anti-ferromagnetic material and ferrimagnetic material. Okay, depending on upon the spin orientation of the electrons. Okay, so already we discussed that. So that if you will take any dipole momentum, it depends on the so orbital magnetic momentum and spin magnetic momentum. Okay, so in case of ferromagnetic material, so it will be depends on both orbital magnetic momentum as well as spin magnetic momentum. But if you will take only ferri and anti-ferromagnetic material, so this magnetic momentum is depends only on the spin orientation. Depending on the spin orientation, if you observe that if you will observe that any orbit, so any orbit contains so positive spin as well as negative spin. So positive spin contain so one direction, that magnetic momentum is one direction, negative spin orientation is another direction. Okay, that's why, so based on those spins, so positive spin and negative spins, so these type of materials will be divided into here. So anti-ferromagnetic materials and ferrimagnetic materials. Anti-ferromagnetic materials and ferrimagnetic materials. First of all, we will discuss about the anti-ferromagnetic materials. So these are the ferromagnetic materials in which equal number of opposite spins with same magnitude, such that orientation of neighboring spins is anti-parallel manner are the present. Okay, So suppose if you will take here, so these are the dipoles are there here. So one dipole is oriented in a below direction, another dipole is oriented in a above direction. That means here mainly due to the spin. Here magnetic field is mainly due to the spin. That's why, so one dipole is magnetic momentum is oriented in a below direction, another one is the above direction. That means equal, whatever the number of spins in downward direction is equal to the number of spins in upward direction. Okay, if both are equal, number of spins, spin oriented magnetic momentum in downward direction is equal to the number of spin magnetic momentum in upward direction. At that case, resultant magnetic momentum is zero. Resultant magnetic momentum is zero. So these type of material we will call it as anti-ferromagnetic materials. Anti-ferromagnetic materials. Okay. Susceptibility is small and positive. Okay, susceptibility of the antiferromagnetic material is small and so positive. The spin alignment is anti-parallel manner. Okay, the temperature at which the antiferromagnetic material converts the paramagnetic material is known as Neal's temperature. Previously we will discuss about that Curie temperature in case of ferromagnetic material. So what happened with increasing the temperature? So at a particular temperature, ferromagnetic material will become paramagnetic material. The temperature we will call it as Curie temperature. Here, in case of antiferromagnetic material, what happened with increasing the temperature at a particular temperature? So that antiferromagnetic material will become paramagnetic material. Antiferromagnetic material will become paramagnetic material. The temperature we will call it as Neal temperature. So here, so chi formula equal chi is equal to C by T plus theta. Chi equal to C by T plus theta. So here T, so T greater than Tn. So when it will become, so T greater than Tn, so it will act as a paramagnetic material. So the temperature we will call it as Neal temperature. The temperature will the temperature we will call it as Neal temperature. So above the Neal temperature, that antiferromagnetic material will act as a paramagnetic material. Below the Neal temperature, so this material will act as a antiferromagnetic material. Okay. Yes, susceptibility is inversely proportional to the temperature. So examples, what is the examples of antiferromagnetic material? So FeO, MnO and Cr2O3. So ferrous oxide, manganese oxide and chromium oxide. So these three are the examples for antiferromagnetic materials. Antiferromagnetic materials. Now coming to the ferromagnetic materials. Okay, so here also same. So how it will be antiferromagnetic material? Some spins are oriented in upward direction, some spin magnetic momentums are oriented in downward direction. But in case of ferromagnetic materials, so those spins are equal. So whatever the upward spins is equal to the downward spins. Okay, but in case of ferromagnetic material, so either downward or upward will be dominate. Okay, so if you take the example, see here in this diagram, so upward spin is, so upward spin magnetic momentum is greater than the downward spin magnetic momentum. That's why there is some resultant magnetic momentum is there. Some resultant magnetic momentum is there. These type of magnetic material we will call it as ferromagnetic materials. Ferromagnetic materials. That means here magnetic momentums, upward magnetic momentums are not equal to the downward magnetic momentums. So that's why there is a resultant magnetic momentum is there. So that's why so these type of material we will call it as ferromagnetic materials. If you observe here, susceptibility is positive and very large. Okay, so the susceptibility of ferromagnetic materials are so high and also it will be large. Susceptibility is inversely proportional to the temperature. Similarly here also, so there is a Neal temperature will be there. So below Neal temperature, these material will act as a ferromagnet. Those material will exhibit the ferromagnetism. Above the Neal temperature, these material will act as a paramagnetism. Okay. Now coming to the, so previously we will discuss now. So how it will be for ferro, how it will be for para, how it will be for, so ferri also, ferri, anti-ferri. here. So ferromagnetic material, ferrimagnetic material, paramagnetic material, diamagnetic material. So this is for vacuum. Okay. Now coming to the ferrites. So we'll discuss about the these ferrites. So next class. So whatever those material exhibit the ferrimagnetic magnetism, those material we will call it as ferrites. So which material exhibits the ferrimagnetism? So those material we will call it as ferrites. Okay. So we'll discuss much more. So in next class. Yeah, I will take the attendance. If you have any doubts, you can ask. Any doubts? Okay, if you have, that means if you have no doubts means you can leave from the session.